Well, yeah, everything is fine now. Okay, so finally we may start. We continue with Bootstrap. Today I would like to talk about some problem solving, to discuss some exercises. So you will have home assignment that you can complete using computers, but on the exam in winter and final exam you will have to solve some problems by hand. So I will provide some problems, and using these problems we will discuss limitations of Bootstrap. So we will discuss lecture 3. We continue with Bootstrap because that's very powerful and real-life technique. But this technique we have discussed mostly computational part. We haven't discussed some theoretical properties. So let's go. Okay, lecture 3. We will do some exercises. Plus we will discuss limitations. And probably, but I'm not sure if we will finish, we will discuss bias. I think probably not the best Bootstrap, but probably Bootstrap that is fast and precise. So we will discuss bias. So we will start discussing bias corrected and accelerated Bootstrap. At least we will start. Okay, so let's start first with the exercises. The main goal of the first exercise is to show the basic theoretical property that if you have some sample, original x1, x2, xn, let's say from uniform distribution with 0 left border and let's say 10 right border, and they are independent, and you create the Bootstrap sample. We are not discussing how to do it. I hope you already understood this. And my main question about theoretical properties, conditional and unconditional. So first let's discuss something like what is the expected value of, let's say, x1 star unconditional, or maybe expected value of x1 star given that you know x1, xn, or probably conditional expected value of x1 star if you know of x2 star, if you know x1 star. What else? We can discuss the variance, yeah? What is the probability? So we can discuss probability, variance. What is the probability that x1 star will be less than t? Or maybe variance of x bar, but oh no, that's boring, variance of x bar, you know, but to compare with, my main goal is compare variance of x bar and variance of x bar star. Maybe that's enough. Maybe we can calculate, so we can calculate covariance of x1 star, so it's related, x2 star, unconditional, and covariance of x1 star, x2 star, given that you know x1, blah blah blah, xn, or probably variance of x1 star, unconditional, and variance of x1 star, conditional, that you know x1, xn. I think that's enough to understand the difference, or big or small difference, between
original distribution and bootstrap distribution. Okay, so the first is just to check whether we can work with all this stuff if someone remembers these E and variances. Okay. Okay, so the first question maybe is more or less intuitive. What is the expected? So okay, we are starting the solution process now. Okay, who can tell me the first one? Yeah, why?
Well, first, we actually have sample.
Sorry, I will note your answer. You are completely right, but why? Yeah, that's great answer. Yeah, perfectly fine. Yeah, why randomly taking random? So we have two sources of randomness here. Maybe it will change. We have one source of randomness at level 1. Nature generates x1, x2. Yeah, that's the first reasoning. So you are right. Explanation. You may say, oh, expected value of x15 is you just enumerate all possibilities and weight them. So you may say that with probability, with some probability, x1 star will be equal to x1, and we multiply by conditional value of x1. If x1 star is equal to x1 plus, maybe we have chosen as a first bootstrap value, we have chosen the second original value, and we multiply this by so in this case, we should calculate expected value of x2 given x1 star is x2, and so on. So basically, that's the decomposition of expected value formula if your omega is decomposed into A, B, and C parts, non-overlapping and covering the whole omega. Then expected value of any random variable W is just expected value of W if A has happened times probability of A. Plus, yeah, you're completely right. That's a good reasoning. Yeah, you're completely right. And in our case, all probabilities are equal to, so that's a general formula, how to decompose unconditional expected value into conditional terms. And basically, in our particular case, all probabilities are equal to 1 over n. We have n terms, so n terms. Every probability is 1 over n. And because the choice of x star is independent of the value of x2, so the expected value of x2 is not influenced by the choice of x1 star. So we can just omit conditioning. So x2 as random variable and x1 star equal to x2 are independent because you are choosing the value as x1 star absolutely randomly. You are not trying to pick up high value. So these x2 value and random variable are independent. So we may omit conditioning, and you are exactly right. We get n terms. Every term is equal to 1 over n times expected value of typical x. And you're right, that's 5. Sorry about this small bump. Okay. Okay, let's move on. Yeah. And what is this value? The expected value of x1 star, if you know the values of x1, x2, xn. Yeah, you are completely right. If they are fixed, we do not treat them as random, then they are x1 plus blah 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 plus xn over n, because we have fixed, we have de-randomized the first stage, the choice of nature is fixed, and we have only one source of randomness now, the choice of bootstrap replication. Okay, what is this value? No, they are dependent. They're dependent. No, it's not 5. Okay, that's a hard question. So let's go back to. So let's. So first, let's speak intuitively. Maybe it is even so. First idea: imagine that you on the second iteration you pick up high number. So probably all numbers created by nature were high. Yeah. Okay. Yeah, and gives information about the sample. Okay. So how we may treat this? Basically, let's do this. So maybe how we can do it. So first point, with probability 1, all values of x1, x2, xn will be different. That's okay? So we may not consider the case when x5 is equal to x7, yeah? Because they are uniform distribution is continuous. So with continuous distribution, you have 0 probability of exact match between two different xi and xk, okay? Okay, so let's assume all x are different. So you know the value of one of them. So with probability 1 over n, you will choose the same value, yeah? And with probability n minus 1 over n, you will choose another value that is independent, okay? So who can tell me the answer? So with probability 1 over n, you will choose the same value. With probability n minus 1 over n, you will choose different value. And with probability 0, some values will coincide, but we ignore this third possibility. So basically, there are two possibilities. Yeah. Yeah, exactly. So basically, we have two possibilities. Either x2 star is equal to the same. So we have chosen the same xi, or we have chosen different xi. So x1 star is equal to, let's say, xi, and x2 star is equal to the same xi. That's the first possibility. And the second possibility is that x1 star is equal to xi, and x2 star is equal to xj. And I ignore the possibility that the x1 star is equal to x2 star, but different original values were chosen because this probability is 0. So plus something with 0 probability. So I ignore the third case. And basically, yes, you are right. I will write the answer here. With probability 1 over n, you will pick up exactly the same value x1 star. And with probability n minus 1 over n, you will pick another value that is independent from x1. And if the value is independent from x1, the average value, the expected value is 5. That's okay? Yeah? Okay. B probably is easy. So that's our answer. B probably is easy. I don't know why I have written it in that order. Maybe it's like original, because x1 star is just the one of the original axes. The probability can be decomposed in exactly the same way. Yeah. So probability can be decomposed exactly in the same way. Probability that x1 star is less than t is just probability that x1 star is equal to x1 times probability that x1 star less or equal to t, given that x1 star is x1, plus the same trick with decomposing the sample space into non-overlapping events. Yeah, the distribution of x1 star is exactly the same. Okay, the distribution of x1 star is exactly the distribution of x1, unconditional. I mean. Okay? Yeah? Okay, let's move on to variance, because variance may be a little bit trickier. We know already the fact from point A, we know that x1 star and x2 star are dependent. Yeah, we already see that this covariance probably is not 0. We know that covariance may be 0 even if the variables are dependent, but the best predictor is linear, so covariance should be non-zero and should be positive or negative, what we do expect intuitively. Yeah, that should be positive. We expect intuitively that it's positive. Why we expect that the covariance is positive? Yeah, the coefficient before x1 star is positive. Yeah, if it would be negative, we expect negative covariance. Yeah. So with higher value of x1, the expected value of x2 star positively depends on the value of x1 star. So we expect it greater than 0. And so this will influence the formula for variance, because variance of a sum, so this fact will influence the variance of x bar star. So the distribution, we see already that the distribution of x bar star differs from the distribution of x bar. It will differ a little bit, but it will. Okay? So maybe we can answer some other questions. What is the covariance? So maybe this, if we have intuition, we can simply answer this. What is the covariance of x1 star, x2 star, given that you know x1, xn? So imagine that x1, xn are constants, 5, 7, 6, 5, 3. What is the covariance? Yeah, because they are, we simply generate, yeah, that value is 0. Any questions? There's one online. I understand that it's hard to be in contact when you are online, but if you have any questions, don't be shy. I'm here to answer you, to help you. Okay? Yeah. Let's finally find the variance. There are many ways to find it. I think the easiest one is the decomposition by sum, because variance respects the sum. the summation. So we know how to work with variance of a sum. So I will use the trick to decompose into a sum. Okay, so let's write that x1 star. I will write it as a sum. Why I will write it as a sum? Because covariance is variance is it's a pleasure to work with a sum when you have covariance. So I will decompose. I will write x1 star as a sum to use properties of variance and covariance. So it will be, let's say, indicator 1 times x1 plus indicator 2. So I will write in the probably strange way, but the main idea, why do I write in such a strange way? It seems that I have created unnecessary complexity. I have introduced I1, I2, IN. So basically these indicators I1, I2, IN are all 0 except only 1. Yeah. So if, for example, second x was chosen as a first bootstrap x star, then I1 is 0, I2 is 1, I3 is 0, and so on. Okay. So for example, if x1 equals to x2, that means that I1 is 0, the first was not chosen, I2 is 1, I3 is 0, and so on. That's okay? So it seems that I have introduced something very strange, but it will be easy to deal with. Okay, so by the same logic, x2 star is equal to some, let's say, k1 times x1 plus k2 times x2 plus kn times xn. These k1, k2, kn, they indicate which original x was chosen in the bootstrap sample. Okay? So now it's more or less easy to write, for example, the variance of a random variable, or okay, let's find the variance of x1 star. Let's find the covariance of x1 star, x2 star, and if we can do that, then the variance of x star bar is just is almost calculated. So let's start with this. Okay, so what is the variance of a sum? Who remembers? Okay, so it's the sum of variances plus covariances, yeah? Okay, so it will be n times variance of typical term I1, x1 plus how many pairs of covariances will we have? So how many pairs? I1, I2, first and second, number 5 and number 10. So we will have C, or binomial coefficient, or we may write it like choose. Yeah. From n, we choose 2 pairs. Yeah. Or if you prefer American way, you can write like this. That's okay. And the types, typical covariance of I1, x1 and I2, x2. Okay, what is the covariance of x1, x2? We need to, when we calculate covariance of 2 sums, we need to take every possible combination. So we need to take every possible combination. So, for example, when I calculate this covariance, I need to calculate covariance of these terms plus covariance of these terms plus covariance of these terms plus covariance of these terms. When I calculate covariance, I need to take any combination, okay? Yeah, but it's more or less obvious that the only possibility to get to see dependent random variables is to include the same x. Yeah. because I number 5 is independent of all k's. Yeah. So we will basically have n times variance of, times covariance of typical I1, x1, k1, x1. Yeah, that's great. Now let's calculate everything. What is the variance of I1, x1? If you remember, the variance of a random variable is expected value of random variable squared minus the squared value, squared expected value of a random variable. We pick the random variables, but when we pick random variables in Bootstrap sample, we do not look at their values. So I1 is independent of x1. So basically, I get expected value of I1 squared times expected value of x1 squared minus expected value of I1 squared times expected value of x1 squared. And I1 is just an indicator. So when you square indicator, what will you get? Yeah, you will get the same indicator. And basically, it's 1 over n, the probability that the indicator is 1, times expected value of x1 squared minus 1 over n squared times expected value of x1 squared. So basically, that's the answer. In my case, probably you remember that expected value of x1 is 5. Maybe you remember the variance of uniform distribution. It's b minus I squared over 12. So in our case, it's I think it's 100 over 12. And so expected value of x1 squared is 100 over 12 plus 25. Okay, yeah. And using the same logic, we can calculate everything else. So let me show how can I calculate these values. Probably I will not finish arithmetics. Maybe I will show only one. So these covariances are different because here they are dependent because I1 and I2 are dependent. And these covariance, these random variables are dependent because x1 is dependent. Okay. So let me calculate which one. Probably 2 is too much. I just like to show how to do this, but probably I don't like to finish all the calculations. Which one seems the most difficult to you? Oh, everything is easy. Sorry? Not easy. Okay, let's do this. But I hope you can at least plug in values, yeah? That's fine. Is it clear why expected value of I1 is 1 over n? Because what is y1? Y1 just indicates that we have chosen the first original value in the Bootstrap sample, and the probability of choosing each particular original value is 1 over n when we pick up bootstrapped values. Yeah. Okay. So let's calculate covariance of I1 x1 and I2 x2. By the same logic, it's expected value of I1 I2 x1 x2 minus expected value of I1 x1, expected value of I2 x2. That's basically the definition of covariance. So now let's check which random variables are independent. X1 and X2 are dependent or not? Original X1 and X2? No, they are independent. I1 and X1, are they dependent? No, because X1 is chosen by nature, is created by nature, and I1 is just indicates which X we choose, but we choose when we choose, we are not looking on the values, okay? We are choosing independently of values. So there are no dependency here, no dependency there, no dependency there, but we have one dependence, which, yeah, I1 and I2, they are dependent. Why they are dependent?
Because they cannot equal.
Yeah, they cannot be both equal to 1. You are completely right, because if you choose the first value as bootstrapped first value, then you are not choosing the second one original value. Yeah. Yeah, exactly. Я забыл. Emil is completely right. If you think a little bit, I1 times I2 is perfectly 0. As I1 squared is perfectly I1, I1 times I2 is perfectly 0. Why, Emil?
Because one of them is 0.
Yeah, one of them is 0. So they cannot be both simultaneously equal to 1. Okay, so the answer here is minus 1 over n squared times 5 squared. So we may decompose it further. I1 times expected value of x1 times expected value of I2 times expected value of x2. And finally, we get here minus 1 over n squared times 5 squared. Okay, so let's finish the last covariance. And I think that's enough, because everything else is just you plug in values, and that's more or less boring. You can finish, but I think that's more or less boring. X1 and K1 X1. By the same logic, we have expected value of I1 x1 squared times k1 minus expected value of I1 x1 times expected value of k1 x1. And basically that is a little bit easier, or maybe not. We have expected value of I1 times expected value of x1 squared times expected value of k1 minus, and here everything can be decomposed into the product. Expected value of x1. Okay. And okay, so let's write the answer. So let's write the answer. The answer will be here 1 over n squared. I may take out 1 over n squared times, and if you take out 1 over n squared, you will see that the remaining term is just the variance of original random variable. So you will have 1 over n squared variance of x1. And it is 1 over n squared times 100 over 12. Okay. And I think we have done. So now we can finish this calculation. What is the variance of x star? Maybe I will go to the next page, because otherwise you will be the order of calculations will be messed up. So variance of x star bar is just variance of x1 star plus x2 star plus xn star over n. We take out n with a square, and inside brackets we have n variances of typical term plus, as we have already calculated, 2 times the number of possible covariances is a choose from n. We choose two indices, yeah, first and second, 5, 5th and 7th, and so on, times covariance of x1 star, x2 star. That's okay? Yeah. And I will not finish calculations. You can finish. That's not a big deal. And you will see that it is not equal to the variance of x bar, but they will converge to each. They are not equal. So if you just plug in, we have already calculated everything. So we have calculated this number, we have calculated that number, and you can see that they are different. But if you try, you can see that the limit, for example, of variance of x star divided by variance of x bar star will be, who can guess the value? Yeah, it will be 1. So they approach each. So they have the same expected value, but the variance is different but close. Sorry? Yeah. And number of bootstrap replications is not here important, because we are basically consider one typical bootstrap replication. Okay. So I'm showing you the level of theoretical exercise with nothing more like properties. So we can use not uniform, but another distribution, and so on. Okay, so 2 more exercises. I would like to show that sometimes bootstrap fails. And you should know about this. I understand that we will not prove asymptotic theorems about bootstrap, but in any case, you should know that sometimes it fails. And the intuition is, there are many cases where bootstrap fails, but the intuition probably, if you have studied some optimization course, you know that there are basically 2 types of extrema. So intuition, why bootstrap fails. So at a very high level, you know that there are 2 types of extrema. Either extrema is internal, or you have, what can you have? No, I think there is internal extrema and internal. No. For example, you are maximizing. So imagine that you are maximizing something like I don't know, some f of x, x. You have some constraint x is not less than 7. So, yeah, and there are internal extrema. And with this extrema, everything is fine. You have beautiful theory that, oh, the first derivative is equal to 0, and you win. And there are corner solutions, okay? So there are internal, that means, like in Russian, внутренняя точка, внутренний extremum. Okay, there are internal extremum, and you may have corner solution. And when you have corner solution, then the derivative may not be equal to 0, yeah? It may, but it may not, okay? And probably you understand that corner solutions, these are, so that's nothing more than intuition, but I will provide some examples. So these are good guys. So internal solutions like are good guys, and these are bad guys. Okay. And Bootstrap fails when you have something like a corner solution. Let's be more specific. So corner solution is a warning. Maybe Bootstrap is not applicable here. That's the idea. And now I will illustrate this idea with some examples. Example 1. Imagine that x1, blah, 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 xn are independent, uniform from 0 up to parameter a. You see already, probably you will have a corner solution, yeah? Yeah. Okay, and my question is, first question, calculate maximum likelihood estimator, and B, what will be the real coverage probability of naive bootstrap calculate the estimator A hat maximum likelihood, and calculate the real coverage probability of naive bootstrap confidence interval with nominal coverage probability 0.95. So calculate the maximum likelihood estimator in this case. Probably you know the answer. Yeah, from the last year we know that. So yeah, we may start solving the problem. Yeah, everything is here. So the first question, A hat maximum likelihood is just maximum of x1, xn. Do you remember this? No? Okay. Okay. So now let's move on to the second question. Imagine big N is big. N is big. Imagine number of bootstrap replication is big. So when I write bigger, that means very big. Double. So you have double sample. Imagine some big numbers, 1 million, 2 millions, 10 millions. That's okay. Okay, what's going on in bootstrap replications? Okay, imagine that I have some original data set, a big data set, N is big. We are not worrying about that. N is small, 3 observations, 3 million of observations. But all these observations will be bigger than A or lower than A. Yeah, with probability 1, all these observations with probability 1, all these observations are less than A. That's okay? Okay, all these observations are less than A. How naive bootstrap works, or maybe does not work. Okay, we create x1 star, xn star. Okay. Maybe just some additional. So, okay, all these values will be bigger than A or lower than A. Because they are chosen from x1, xn, all they will be with probability 1, they will lower than A. Okay? Okay, now how you construct A star hat? How you construct A star hat from a bootstrap sample? You use the same point estimator, but you apply it to the bootstrap sample. Exactly, xn star. And this A hat star if all they are less than A, yeah, it is also less than A. Okay, how naive bootstrap works? We write them, we note them on a line. We emit, so let's discuss naive bootstrap. So let's emit lowest 2.5%, highest 2.5%. Okay, this will be our left quantile of A hat star and right quantile of A hat star. And what will be the probability that our A will be covered by this empirical bootstrap confidence interval? Yeah, it's exactly 0. Okay? So sometimes bootstrap fails. You should know it. When you have something like corner solution, that's a bad case. Even this estimator is consistent. By the way, the point estimator is okay. The point estimator, it is biased a little bit, but the bias disappears. The probability limit of A hat maximum likelihood is fine. So as a point estimator, it is biased, but more or less fine. It is consistent. But bootstrap confidence interval miserably fails as 0 instead of 95%. That's okay? And probably maybe just as a problem, and what is the probability that so let me just formulate. Oh, that's funny additional question. What is the length? What is the length? Oh, probably the width. Yeah, the width. What is the some additional question? What is the width of? What is the width of? Just let me say. Width of. What is the width of, let's say, 20% naive bootstrap confidence interval? So if I will, what is the width of? Well, that's very particular, strange example. What is the width of this? So that's a funny number, 20%, but what is the width? Understand the width? Yeah. Yeah. What is the width of 20% naive bootstrap confidence interval in this case? Width, yeah. The width, the width, the width, the length. Okay, so once again, let's look. What will be the most common value of A hat star? Okay, let's solve C. What will be the most common value of A hat star when you do replications of original sample? Yeah, because you are choosing a lot of x's. Yeah, with high probability you will pick up the biggest one. I don't know where the biggest one is located. Yeah, and yes, we take them with same probability, but you have a lot of chances. So, Okay, so let's calculate what is the probability that A hat star will be equal to maximum of x1 xn. So what is the probability that A hat star will be equal to A hat? What is it? Maybe it will give you a hint. In what situation A hat star will not be equal to A hat? When we have not chosen the biggest element. Yeah. What is the probability that we haven't chosen the biggest element? You should not choose it on the first iteration. You should not choose it on the second iteration. Okay? And each time n minus 1 over n times n. Okay? Okay. So it is 1 minus 1 over n times n. And we say that n is big. Yeah, so probably you recognize here. So probably you recognize here the famous. So probably something famous here. Yeah, 1 plus 1 over n power n goes to e, and 1 minus 1 over n power n goes to 1 over e. Okay, so that's approximately, if n is big enough, that's 1 minus 1 over e, so that's approximately, let's say 60%. So that's approximately 60%. So 60% of time you will get the same values will be generated. So honestly speaking, this distribution will be very, very strange. That's not probably the good picture. So probably a lot of time you will choose this value, and 40% of time you will choose other values. So with high probability you will choose. So this is A hat star. This is A hat. Yeah, that's okay. So A hat star is very degenerated. In many cases, you will get exactly the same value. Okay, and if you are trying to create 20% naive bootstrap confidence interval, you will emit 40% from the left side. But 40% from the left side will be, we will emit all of them. Yeah, 40% from the left side. Yeah. You will emit 40% of the right side, but there are many observations in just one point. Yeah, 40% there. And the width of 20% naive bootstrap confidence interval will be equal to 0. Okay? So that's a very strange case, and you should be ready to such problems. Okay, let's do one more problem that shows that bootstrap fails sometimes, not always. So bootstrap is a very widely used method, much more used than standard confidence interval because it's more robust. So that's our friend. But you should know that sometimes, so you should not be blind about bootstrap, but use it. Yeah. Okay, and you have, so imagine you have 1 million of observations. So let's say 100 of observations. So 60 observations are in one point. 40 observations are to the left. If we are trying to have 20% coverage probability, then you will emit 40 points from the left, 40 points from these 60 points, but all these 60 values are in one point. yeah, 40 of them will emit it, 20 of them will be there, but they will lie at the same point. Sorry? You will have 20 observations that are concentrated in one point. And if you try to calculate confidence interval from the lowest remaining point to the highest remaining point, you will get 0. So it will be interval like from 7 to 7. Okay? So let's consider one more example. Imagine that you have x1, x2, xn that are, oh yeah, they are very good. So corner solution may be not corner in terms of distribution, but in terms of possible values. Let's say 1. Okay, and we have additional information. It seems that additional information cannot hurt. So we have additional information. We have information that mu is greater than 20. From one point of view, oh, that's good. That's some useful stuff. Yeah. Okay. So first question: how will you estimate, given this additional information, how will you estimate? Mu hat by maximum likelihood. Okay. So first question is how will you estimate mu hat? So what's your answer? Yeah, obviously, without this restriction, the maximum likelihood estimator is just, without this restriction, yeah, it's x bar. We have a very nice situation, normal distribution, independent. So that's a perfect example when all classical tests are valid. Okay. Okay, without this restriction, we will have x bar as our maximum likelihood estimator. But when we have this information, if it happens that the average is lower than 20, then we cannot estimate by 20 as this forbidden. Yeah. So we will write maximum of this value and 20. That's okay? And this estimator is perfectly consistent. Yeah. So for example, if you try to calculate probability limit of mu hat maximum likelihood, because maximum is continuous, probability limit goes inside maximum, and you will have so it is so you may calculate it. It's because probability limit enters continuous functions, then it's maximum of probability limit of so it will be maximum of probability limit of x bar and 20, and that's probability limit of x bar by law of large numbers is equal to the mu. And we see that if mu is bigger than 20, it's equal to mu. If mu is 20, it's also equal to mu. Yeah. So it's always equal to mu for all mu from 20 to plus infinity. So that's a consistent estimator. So we have used additional information. It's consistent. It's the best what we can. But let's look once again at the situation. Imagine that mu is 20. Imagine that mu is on the border. So imagine that n is big, number of bootstrap replications is big, okay? And now let's calculate the probability that we will cover. So let's try to understand the real coverage probability of 95 naive bootstrap confidence interval. So what will be the real coverage probability of 95% naive bootstrap confidence interval? Imagine big N, big number of replications. That's not a question. Okay, so maybe I will add some more questions, hints, like what is the probability that you will observe X bar higher than 20 in point C? In point C, you have that's a true value of mu. What is the probability that you will observe X bar bigger than 20? Yeah, it is 1/2, because if xi has distribution mu and 1, then X bar has which distribution? The same expected value, you're right. How variance is scaled when you go to the average? 1/n, yeah? Okay, and hence what is the probability that here mu equal to 20 is the real value of mu? Imagine that the God has created mu equal to 20, and I, the researcher, I'm trying to build a confidence interval for this mu considering naive bootstrap. Okay, so that is exactly 1/2. That's okay? Yeah? So with the probability, so let's consider two cases. The first case, if so the first case, with probability 1/2, the nature generates x1, xn such that X bar is lower than 20. With probability 1/2, the nature generates the sample with X bar greater than 20. Okay, let's think a little bit. What is the probability that, so let's speak, how much time do we have? Okay, we have a little bit of time, let's 4 minutes. Okay, so let's probably, how do you think the real coverage probability will be bigger than 95%, lower than 95%? How do you think and why? Maybe it's better. So let's at least compare it. So probably the calculation is long, but at least let's compare it with real probability and the actual nominal and the real. So which one is bigger, why? So let's understand. Some values. The lower bound, the lower interval will be less than 20. I don't get, and why that means that the real coverage is lower than maybe the right border of interval is big enough, because here values will be different. Yeah, they are normally distributed, so they do not coincide. Okay, so maybe once again a question hint. Okay, so, and what is the probability that x star bar will be bigger than 20. Okay, so let's do like this. What is the probability when, so what is the probability that x bar star will be bigger than 20? Yeah, why? Why it's 1/2? Because everything is, I will say, because everything is symmetric around 20. Yeah, because when we, because of the symmetry. Yeah, I will say because of the symmetry, because every x1, x2, x3, x4, x5, they are symmetrically distributed around 20. Yeah, yeah. If we pick up x1 star, x2 star, x3 star, they are symmetrically distributed around 0, or around 20. Yeah. Okay. We calculate the average, but if we multiply every x by, so we reflect it around 20, so the distribution should not change. So the probability should be 0, and the probability of obtaining exactly 20 for normal distribution is 0. So it's 1/2. Okay. Yeah. So basically, with probability that mu hat star will be equal to 20 is 1/2. It follows if you have with that's okay. Yeah. And you feel well that that's a bad sign for confidence interval, because so we can already see, for example, I wish a very small confidence interval with low coverage probability. Imagine that I wish 25% confidence interval. So I will try to create 25% confidence interval. I cannot get it. I will get 50% confidence interval at least. Yeah? That's okay? Because with probability 1/2, I will pick the exact value at least. Yeah? With probability at least 1/2, I will pick the exact value. Okay, so we see already that we have not probably finished, but I hope you can finish it with simulations. So these problems are hard in general to calculate real coverage probability. So we see already intuitively that real coverage probability is at least higher than 1/2 for all nominal coverage probability. Yeah, you cannot, you always include this 1/2. Okay. Okay, that's all for today. We have seen that Bootstrap is, so we have calculated, so that's the level of problems we will have on the exam. Once again, some problems will be standard, so you can, so I think when you are on the final year, I don't want to fire you, and so some problems will be standard if you have solved everything. So you are more or less on a risk-free side. And you will have simulations in your home assignments. So that's all. Let's finish.